In this question, it asks or states, whiskey stones are made up of soapstone, and when frozen, they can rapidly cool a solution. A scientist uses a whiskey stone to cool an espresso. So they're using a small rock to cool a cup of coffee. And so we would like to know, what is the final temperature of the espresso created in Celsius? If the espresso is 75 grams and 73.8 degrees Celsius, and a single whiskey stone weighing 26.91 grams at negative 15 degrees Celsius is dropped in the espresso. Espresso has the specific heat capacity of water, 4.184 joules per gram Kelvin, and whiskey stones have a specific heat capacity of 6.981 joules per gram Kelvin. So in this question, kind of like the drawing in the top, what we're really asking is, how does the heat transfer from the cold stone to the warm liquid result in a final temperature? So we know that heat, so Q of the stone plus Q of the coffee equals 0, because the heat that leaves the coffee goes into the stone, so they will arrive at the same final temperature. So Q of the stone equals negative Q of the coffee. And you could have put the negative sign on the stone or the coffee, just not both. It's one or the other. And so Q, in this case, equals M C sub S delta T. So we can set up both of ours. And so I'm going to put the stone on this side and the espresso over here. So the mass is 75 grams. C sub S is 4.184. Ti is 73.8, and Tf equals unknown. On the other side, the mass is 26.91 grams. The C sub S is 6.981 joules per gram Kelvin, and Ti is negative 15.0, and Tf equals unknown. So now we can set these two equations equal to each other, where we have 26.91 grams multiplied by, we need to move this so that we have more space. 26.91 grams multiplied by 6.981 joules per gram Kelvin times Tf minus negative 15.0. That equals negative 75.0 grams, 4.184 joules per gram Kelvin, and Tf minus 73.8. Sorry, it gets a little tight on the side. So now what we're going to do is think about how we can handle this in such a way. So there are specific equations that you might have seen that combine all of these variables. Personally, I find the algebraic approach of gathering like sides or like items together and setting it up. So you can do this in a variety of different ways mathematically. So now on the left side, I'm going to multiply these two numbers together and distribute it over the things in the parentheses. So I have 187.9 TF plus, because a negative times a negative is positive, 2817.9. So what I did is 187.9 times TF plus 15.0. And I've increased the number of significant figures just to make the math a little bit easier. So we're going to do the same thing on the other side, and I got negative 313.8 TF plus 23,158.4. So now I'm going to move the TFs to one side, and I get 501.7 TF equals 20,340.5, and TF is equal to 40.5 degrees Celsius. So I'm going to make this a little smaller so we can look over the whole thing at the same time. So in this calculation, what we're really looking at and trying to measure is how does the whiskey stone or the cooling stone cool the coffee? And you can see that it doesn't get all that cold, but it did drop 25 degrees. So when we set this up, we know that the heat that leaves the coffee goes into the whiskey stone, so we can set those equal and opposite to each other. And then we just track the variables, and then we need to do some algebra. And the tricky parts here are keeping track of our negative signs or thinking about when a negative times a negative or minus a negative number turns into a positive number.